Just a moment. Yes, okay. Thank you very much for inviting me, Taira Sensei, and especially for preparing the nice party after this. So I really I will enjoy that. Okay, now I'm going to present about excitation emission matrix, EM, or fluorescent fingerprint we call it, for the discrimination of the 1 MCP treatment on apple fruits. And this is one result from the math project. And what is 1 MCP? It has a long name. It's an ATN inhibitor, and fruit freshness can be kept long with this chemical. And for apples, the use of 1 MCP is rapidly increasing in decades. And especially for the orange cultivar. Orange cultivar is Japanese apple and with a green skin. And for this orange cultivar, 1 MCP can reduce hardness, acidity degradation during the preservation, and also it can prohibit burning disease. So, and it is said that its effect is equal or higher than the controlled atmosphere CA storage. And now there's a need for the discrimination by the third party on the 1 MCP treatment because they would like to know the fruit is proprietary treated or can be stored for long and so on. And also some countries, including Taiwan, banning the use of 1 MCP. And Taiwan is a very important country for Japan because this is the main customer of the Japanese apple exporting. But the conventional analytical method for the 1 MCP treatment is GCFID, so which takes time and takes long the technique. So we would like to know the use EM for the discrimination of the 1 MCP treatment. And this is a sample, so orange from Onway Prefecture, 280 fruits and 140 treated and versus 140 control. And the storage condition is normal storage at 0 degrees C. And this is the storage, so from 0 months to 8 months, and half control and half 1 MCP treatment. And this is how we measure EM. So we measure the EM on the skin of the apple at this point and this point, so left and right hemisphere. And we use the FE 8500 from JASCO with egg fluorescence unit. So we place the fruit on the top of the egg fluorescence unit, and the surface is shined with the excitation light, and the fluorescence is measured with this machine. And this is an example of apple surface EM. So this is average of each fruit, control and 1 MCP. And this is X as excitation wavelength and Y as emission wavelength. And the color indicates fluorescence intensity. So red means very high fluorescence. And you can see there's almost no clear difference between control and 1 MCP. So of course we use chemometrics. So this is a score plot from the PCA, and we use pre-processing of normalized and mean center. And in principal component 4, we could see some separation. So we thought that maybe we can discriminate these samples with further discriminant analysis. So we tried the PLSDA. This is a flowchart of the discriminant analysis. So we have EM data, and we separate this into training and tested, so 60% versus 40%. And we try to pierce DA with a cross-validation of lambda subsets with 10-fold with 10 iterations. And then we predict the treatment, which is control plus 1 MTP. And then we optimize a model with a 6 combination of preprocessing, and also we try to select variables. And when we get the best model, we apply this model to the test set, and we check the accuracy of the discrimination. So this is the details of the model optimization. So we use these kinds of preprocessing, and also we try to select variables because it is said that excluding variables not contributing to the model may increase the accuracy of the model. And we use the criteria of VIP or SR. VIP is variables of importance in projection, and SR is a selectivity ratio. And in this slide, I show only this. And this is how we select the variables. So first, we develop the PSDA model, and we keep variables with the kth highest selectivity ratio. And then again, we try the PSDA. And then we check the cross-validation error. And then we repeat this procedure again and again. And this is the result. So x-axis is the number of the variables selected using this method. And y-axis is a classification error. So the lower is better. And with this direction, we reduce the variables. So this is started from this number, so over 2,000 variables, and then we reduce the variables, and at this point, the error reached minimum, which is 8.33%. So this is the best model. And this is the red circles are selected variables. So the number of variables are 65. And the best preprocessing was normalized plus mean center, and the number of latent variables was 8. And which was interesting is that the selected variables are not located on the top of the fluorescence, but the skirt of the fluorescence peaks. I don't know why, but it is interesting. And then we apply the best model to the test set, and the classification error was 7.59%, so good. And this is summary. So it is possible to classify the Apple 1 MCP treatment using the EM. And the test set error was 7.59%. And future works maybe for the application to other variables, and we would like to know what constituents contribute this discrimination. And yeah, actually we tried some researches further because some samples were shared with LC-mass and NMR metabolism. And we tried the same variable selection to this data, LC-mass and NMR. And also, we tried to combine the EM, LC-mass, and NMR data. And we combine and we apply the auto-scaling, which means make everything mean of 0 and standard deviation of 1. And then try PCA on that fusion data. And this is the result. So this is a PCA score plot. So we have a clear separation. And this is a loading plot, including EM in red, LC-mass in green, and NMR in blue. And we think that these indicated variables are linked together. They should have some correlations. And maybe we can find something like a mechanism on the discrimination. But there are too many candidates for these kind of data. For like for one variable, we have something like 20 or 30 candidates, so we couldn't identify them yet. Sorry. And this is one story, and then I prepared another example. This is for Aomori. Aomori is a spirit in Okinawa, and we used 39 samples from 8 districts, and in which 16 is new and 23 is aged, and in which 33 is atmospheric and 6 is vacuum distillation. And we used EM measurement. We measured EM using this equipment, Aqualog from Polybar. And this is EM examples. So brand A, brand B, brand C, and excitation wavelengths, emission wavelengths. And this is new, middle, and aged. And apparently, there is a region where the fluorescence intensity decreased from A to C and increased D with aging. And actually, this B and C is a fluorescence from 4-vinyl glycol, 4VC, which is rich in the new Aomori, and it smells like how can I say, smoke or charcoal or something like that. And D is correspond to vanillin, which is the sweet smell, and this is rich in old Aomori. So this is consistent with previous studies on Aomori, also with OVG decreases with aging and vanillin increases. And we tried a PCA on that data, and circle is new one, and square is old ones, so we could separate clearly. And also interestingly, the white ones are vacuum distilled samples, and it seems vacuum distillation samples cannot be aged because even the old vacuum sample is located in the new sample region. So maybe we can use this excitation emission matrix technique to predict aging period or something on the Aomori. Okay, that's all. Thank you very much.
Can I ask you something?
Yeah.
In the apple, okay, are you measuring MCP? Is that's not fluorescent? Or?
No. We are not measuring one MCP because one MCP treatment is done with very low density, and of course they are gas, so they are cold.
Yeah.
So we think some metabolites changes with this treatment, but we are not sure.
Have you tried measuring in like a solution or something of the apples? I mean, a simpler.
Yeah. You mean the juice? Or?
Yeah, something.
Yeah, we tried, especially for NMR and LC-mass juice, but we couldn't find that.
I have one more question.
Yep.
In the data fusion you had perfect classification.
Mm-hmm.
So that would be even better. It's not very practical, but it seems like you have a better.
Yeah, but this is using the LC-mass and NMR,
Yeah.
so it's of course perfect classification, but it's not practical.
No, of course. Okay. Yeah. That's
I'm a bit curious to this MCP. How do they do that? How to, is this, they put the apples in gas?
Yeah, that's right.
Gas in a room for
Yes, in
light?
the room, yes.
Okay.
Yeah, it's gas. And I'm not sure that in detail, but they store the apple in the room and gas inside.
How about apples you buy in Japan? Are they treated with MCP?
Yeah, that's right.
And all the other ones are treated with modified atmosphere, right? I mean,
The combinations.
yes.
So, yeah.
It's normal.
But how is this MCP? Is it used in other countries as well? Is it the same
Yeah,
thing?
sure. The use is increasing, but some countries still bans it.
Yeah, well, I think many people, I don't want chemicals on my apple. I mean, like...
Yeah, sure.
Yeah.
何かあります。OK、じゃあどうもありがとうございました。
ありがとうございました。
すいません。